Hi guys. So we're going to go through an example today where using the principle of virtual work will enable us to actually determine some displacements on a structure. Still probably seems a little bit confusing quite how that's going to work yet. So let's just recap where we've got to and how we're going to move forward. So we introduced work energy methods. And we found that work energy methods almost immediately were limited in what they could do. So with work energy methods, just plain old work energy methods, we can only get displacements if there happens to be a force already acting on the structure somewhere. And secondly, if we have more than one displacement, then we haven't got enough information to solve the problem. If we have more than one force and associated displacement, there's too many unknowns for us. That's too many unknowns. That's my awful handwriting. But this first one here, we can only determine displacements where there's an external force. Explicitly, this means we can't use this so far to work out the displacements that we require for the force method. And the second one here means that even for some quite simple problems, we can't determine displacements. So I'm going to draw a problem similar to one of the problems we've got in the accompanying notes. And I'm going to half solve it today and then probably finish it off in another lecture. So let's say that we have a triangular structure. It has one built-in support and one roller support, and it's joined in the center here. There's two applied forces. Just checking, I think my nomenclature is actually slightly different to what it is in the accompanying notes, but that's the beauty of what you guys have to be able to learn and interpret, is understanding the problems can be written differently sometimes, and that's just it. So we've got four nodes, A, B, and C, and node D. And then I'm going to number these 1, 2, 3, 4, and 5. So let's say if we want to determine the internal forces in the structure, it's statically determinate, so we can get those just as a function of P1 and P2. Let's say we want to determine the displacements in the direction of P1 and P2. So we've got this displacement. Node D would move to the right, and this would be delta dx. Okay, node B would move down, and this would be delta by. Now we know that from work energy principles, the external work, not virtual, would be half P1 multiplied by dx plus a half by multiplied by P2. And we could work out the internal forces, we could work out the sum of internal energy, but because we've got two unknowns, we can't solve this problem. And that's got to be equal to the sum of the internal energy. Now we could work this out. The internal energy, remember, that's just going to be equal to the sum of half of every internal force multiplied by every extension of every member. So we could work all of these out. This would just be a function of these external forces, P1 and P2. And we could solve this, but because we've got two unknowns, we don't know the relationship between them. So the way that we solve this problem is through the application of virtual forces. I said sequentially, I just mean we've got to apply them separately. I probably should just say separately, actually, because we could do P2 first. We don't have to do them in that order, but we're going to apply forces at P1 and P2 separately and work out the internal virtual forces and the associated internal virtual energy. So again, it'll become clearer when we go through more of an example, but let's just go through our procedure that we're going to use to solve this. So the way that we're going to solve this problem okay, so one, this structure is statically determinate, so we can immediately get the reactions. So the reactions on our structure, there'll be a Y reaction, a Y reaction, and a Y reaction up here. So we've got three reactions. We can determine the reactions as a function of the external forces. In fact, let's I'm going to bring this down a second. Actually, I'm going to rewrite this down a second. I'm going to rewrite this down, but I want to just put a definition in here. We'll say that R is a vector of reactions, and so that's going to be RAX, RAY, and RCY for our problem. Okay. And then we've got some external forces, which we'll say is F vector. This is, well, I'm just going to say the external forces. I'm going to actually define what this is a little bit later, because we want to be smart when we use work energy methods, and we're going to put some extra forces in here. And then lowercase f is our internal forces. So now I will actually do the solution procedure, the bit that I said I'd write. So the solution procedure, the first step is to determine the reactions as a function of the external forces. Okay, once we've got the reactions and we know the external forces, then we can determine the internal forces. Okay, so for this problem there would be 5 of these, so this would be F1 through 5. Okay. Once we've got the internal forces, we can then work out how much each member expands or contracts under the real loads, okay, which is for our problem P1 and P2. Okay, delta L And delta L is simply equal to the internal force multiplied by the length divided by the Young's modulus multiplied by the, divided by the Young's modulus and divided by the area. Okay? So these real extensions contain all the information that we need to know about how those external forces actually affect the structure itself. So let's just remind ourselves of these steps. This one is just a free body diagram. This one is the method of joints. And this one is just simply delta L is FL on EA. And this just comes from the definition of stress and the definition of strain. Okay, and then Hooke's law as well. Join those together and we get this one here. So we can do this so far. We haven't got any virtual forces. What we're now going to do is say, okay, we want to determine the displacements P1 and P2. So we would apply in isolation a virtual force at either P1 or P2. And when we apply that virtual force, all of the other forces are equal to 0. Okay, and then once we've got that, this results in the internal virtual forces. We'll call these F star 1 through 5. Now, what we can see we're going to have to do here, this is provides our virtual forces. We're going to have to do again free body diagram and the method of joints. Okay, but whereas previously we'd have known values for P1 and P2, we're going to do it separately with P1 equals 1 and separately with P2 equals 1, and we'll get all of those internal forces. We then take those internal forces and multiply each internal force by the actual extension. And what this results in is the internal virtual energy. This would be in a given member. So the internal virtual energy is equal to the internal virtual force multiplied by the actual extension. We're then going to add all of these UIs up. So for 5 members, we're going to have 5 of these, add them all up, and that gives us the total internal virtual energy. And that's got to be equal to the sum of the external virtual energy. And from the definition of what this is going to be either, say we picked P1 first, multiplied, sorry, let's do this, let's say it's P1 star. Okay, so we just put a virtual force of P1 is equal to 1 Newton multiplied by the delta, and P1 was associated with delta dx, okay? So this would be delta dx or P2 multiplied by delta by, depending which force you've actually applied. And then because we know that these P1 and P2, we just choose them to be 1 Newton, resulting sum of internal virtual energy is just equal to the displacement that we care about. So hence we can solve for that, and then we've got the answer that we want. Okay, so if we start with P1, then we would get delta dx. We'd then go back up to here. We don't need to bother doing this bit again because we've already got the answers. We then change the force that we apply, work out the different internal virtual energy, multiply it by the same, work out the different internal forces, multiply it by the same actual extensions which we have from the real loading, and then add it all up together and we get the opposite, we get the other displacement out. So if we've got this problem here, let's put some numbers in and let's actually solve this problem. So let's cut this out. So let's solve this problem. So we're going to solve this for, let's say, this height is 10 meters. Let's write that properly, 10 meters, and the base is also going to be 10 meters for this case. Let's say we've got a Young's modulus of 180 gigapascals and a cross-sectional area of 15 centimeters. Okay, is that all we need? Let's say P1 is equal to, because I've done all these calculations before, I want to just check that I'm writing down the same answers. P1 is equal to P2 is 500 kilonewtons. And what I'm going to actually want to solve is not just the vertical displacement, I want to know what is the total displacement of these two nodes. So that's our first question. What's the total displacement of B and D? Second part, they're going to say, what if C was replaced with a built-in support? Okay, so the reason I'm going through this problem, I'm going to solve this in a couple of lectures, I think, because this first one's pretty easy. This next one's actually kind of hard to do. Have to heavily rely on coding to help us out with doing this, just because it's so laborious going through the process over and over again. Now, whenever we start a problem, we know we're going to have to use virtual forces. Before we start the problem, let's think about all of the forces that we need to apply. So let's go down here. Okay, think carefully about all the forces that we might wish to apply over the course of a problem. We've got to remember that any displacement we want to know will need some sort of force there at some point, and it will at some point need to apply a virtual force wherever we want to know a displacement. So put them in at the beginning, do your free body diagram and your method of joints completely analytically, and then you can just change the values for either being 0 or 1 when we do the problem. Okay, so I think it's smart to just want to solve a free body diagram and method of joints once. So let's have a look at the problem. I'm asking here, what is the total displacement of D and B? So we've got P1 and P2. This tells us that we're going to have to apply forces at the X direction in D and at the Y direction in B. Okay, we know those because those are the actual applied forces here, and we're told that they're 500 kilonewtons. This one here says what's the total displacement of D and B, so I actually also need to know the horizontal displacement of this part and the vertical displacement of this one, which means I need to be able to apply both horizontal and vertical forces at both D and B. And I'm also, if I'm replacing this with a built-in support, I'm going to need to use the force method to get the redundant support at C. So let's think about all of these forces we need to apply. So we've got, I'm going to put them on in purple. These are places where we could be applying forces. This is FCX. This one up here, let's call this FDY. I'm going to just write over the top of this, I'm going to say this is FDX. I'm going to say that up here, I'm actually, even though P2 is going downwards, I'm going to put this as FBY to be consistent with sign convention. And this one here is FBX. So that means my sign convention gives me Y and X here. Okay, and the reason for doing this is that when we apply P2, we'll apply it as a negative number. And then this should show us, it makes sense that if we're pulling from here, the displacement of B should be downwards. So we'd expect a negative number out. If we didn't do that, we just have to think about the correct direction for all the displacements. Whereas if you're consistent with your sign conventions, then you're good. So let's just go back here. So the total displacement of D and B, this gave me two extra forces to apply, and then C, I've got another force to apply here. So we've got 1, 2, 3, 4, 5 forces on here. Okay, so now we've got those. Let me get rid of this bit. I don't need all that text anymore. We then want to solve the free body diagram and method of joints for this complete structure using the parts that we've got on here. Okay, so I am going to rattle through this fairly quickly because you guys should be quite comfortable with free body diagrams and method of joints. Annoyingly, I've written the reactions with F's. They should have been R's. Doesn't really matter. I'll keep them as yeah, that's fine. I'll keep them as F's for now. They're all just forces in here. That's fine. Okay. So I've now got my reactions on the entire structure, just as a function of any loading. So I can apply either my forces, which I've got. So I'd have a P1 here, P2 here, and I can get all of my reactions from them, or I can apply my virtual forces here and get my reactions as a function of them as well. So that's my free body diagram done. Okay, so I've got 1, 2, 3, 4, 5 equations that I've got. Well, I don't have to use them in that order, but I've got to calculate that one before I can calculate this one. Okay, otherwise they're all just a function of the reactions. But I've got 5 equations that I can get my internal forces now as a function of the any sort of loading on this structure. So I've already coded this up, and I might share this with you guys. I might leave you to go through it on your own. If we've got the applied loading of 500 newtons, let's work out our real extensions inside each member. .500 kilonewtons, then that's equivalent to Come on. There we go. Okay, so that's going to be equivalent to P. Remember, P1 is up at the top. So that would give me, let me just have a look at my proper diagram. Okay, so Fdx is going to be equal to 500 and Fby is going to be equal to minus 500 kilonewtons. So what we have here, this is our real loading. And we can use this with equations we've developed to look at our reactions and then to determine all of the internal forces. Now, I'm not going to go through and calculate each of these, I'm just going to give the numbers. Okay, and the real reactions that we have, we've got the reaction AX, which I called FAX earlier. Let's call it FAX. Let's say FAX is equal to minus 500 kilonewtons. FCY is equal to 750 kilonewtons. And FAY is equal to minus 250 kilonewtons. Okay, let's just check if this makes sense. Once I've written equations like this, I like to just check, do all of my equations result in force balance? So we would have 500, 500, 750, minus 250, and minus 500 here. So we can see that these two cancel out nicely, and yes, these give us, when combined with this one up here, we get the correct moment. We can also see that these just give us zero y force in here. So I just like to check that they all make sense. Okay, so we've got our reactions. Again, this is all stuff that you guys should be good at already. With those reactions, we can then use those in conjunction with these other loads up here to determine the real forces. This gives us real forces of, let's put, remember, force, and then I'm going to put DL. Okay, 1, 2, 3, 4, and 5. So using these equations, I can get all of my internal forces, and then using DL is equal to F L on EA, and then the length just comes from the geometry of the problem. We can get all of those. So I'm going to write these down. We've got internal force is 279.5 kilonewtons, 375 kilonewtons, 500 kilonewtons, 375 kilonewtons, and minus 8.5 kilonewtons. Now these give us 11.6 millimeters of extension, 6.9 millimeters of extension, 18.5, 6.9, and a contraction in member 4 of minus 34.7 millimeters. Now let's just check these numbers, see if these, because again, I've put these equations into a piece of code and run it, and I want to check whether they actually make sense or not. So this is always a good idea to do. We'll pick a couple of places to determine our forces. So we already wrote the reactions over here. I can just put the reactions back up on this problem here. Let's put the forces on as well. So we've got 500. I'm going to write everything on in just in terms of newtons, sorry, kilonewtons. FAY is minus 250. FCY is 750. FAX is minus 500. Just that way. So let's just pick some of the forces and see if they make sense, okay? This angle in here is alpha. Alpha for these is going to be 60 degrees. It's an equilateral triangle. So, sorry, no, it's not. It's not going to be. It's not going to be that. It's not an equilateral triangle. It's not going to be 60 in there. So alpha is going to be equal to, for this problem, of 10 and 10. Okay, that makes sense. Well, there's a couple of things we can see here, that there's 500 down here, and then 3 is in tension of 500, so that's good. Let's just check some of these other numbers here. So let's just pick out joint, this is joint C. We've got 750 in that direction. This is telling me I've got a compressive force in, sorry, no, telling me I've got a, I got those two forces the wrong way around up here. These two forces are the wrong way around. Like, this is why this didn't make sense to me. I've read them out in the wrong order. Okay, so this would be, let's swap those over. Knew those numbers didn't quite look sensible. Now, that makes more sense to me. 4 should be in compression here because it's being pulled here. And that makes sense. So 4 should be a compressive force, and it says that it's a force of 838.5. And we've got a tensile force in member 5 of 375. So these forces, and this is alpha here, let's just check. Well, for vertical equilibrium, 838.5 multiplied by cosine alpha should be equal to this. Yeah, I'm fine. I was being stupid there. So this force here has component cosine alpha, sorry, component sine alpha acting downwards, and a component cosine alpha acting in that direction. And cos of 63.4, whatever that number is, 43 multiplied by this gives me 375, and sine of this angle gives me 750 here. Okay, so I'm just checking these numbers, checking they're sensible. I'm happy with that. Okay, so let's get rid of these. So we've now got all of these numbers here. Now these are our real extensions of the real structure. Okay, and these are the bits that we're going to use to determine our internal virtual work. Now, the bit that we need now is to apply virtual forces at P1 and P2, and then we're going to determine on P1, P2, and also the other two directions that we spoke about, and then we're going to be able to determine the total displacement. So I'm actually just going to do one of them. I'm going to look at trying to determine the vertical displacement here. So I want to apply a virtual force, FBY, equal to 1 Newton. And that's going to tell me what happens to this, that's going to then just tell me the vertical displacement. So we're going to look at that. So what we're doing now is we're firstly going to look for the vertical displacement of node B. So for the vertical displacement of node B, we have a virtual force F By star is equal to 1 Newton, and everything else is equal to 0. So F Bx, F dy, F dx, and F cx are all equal to 0. So we take this here as our only loading, and we then go back to free body diagram, work out the reactions, but we've now just got a single Newton going vertically. It sort of makes sense from symmetry. These two should be equal to -1/2. Okay, if we have a single Newton virtual loading, we're going to have a -1/2 on each of these, but we'll check with our equations whether that gets the right answer. We then do the method of joints to go through. I've managed to draw over this somehow, and we'll get the 5 virtual forces. So if we solve for those, let me have a look. I haven't done this calculation on here yet. Let me... Okay, yeah, so as I suspected, the force to reactions FAY is equal to FCY is equal to -1/2 A Newton. These are our virtual reactions. Okay, and these are just using the same equations that we had before. And then the virtual forces, we get F1 is horrible number, 0.559, and it's going to be symmetric. So we also have -0.25 -1 Newton, 0.559 newtons, and -0.25 newtons. So this is a nice symmetric distribution, which is what we expect with a symmetric structure being loaded symmetrically. And importantly, the member that's just directly above where we're applying this force has the correct sense force in it. So we're applying a vertical force of 1, we'd expect this member to be -1, meaning it's in compression. These are our internal virtual forces. And now we want to know the internal virtual energy. So we can remember that real internal energy is equal to 1/2 of a force multiplied by displacement. This is real internal energy done by a real force. The internal energy that's virtual is equal to the force that's virtual multiplied by the real extension. So this virtual force are these forces we've got, and the DLs are these numbers up here. So we take each of those forces, we multiply them by each of the extensions, and then we get the real virtual forces. Sorry, not real virtual forces, we get the virtual work. So let me print these out as well. Because I've done this all with code, I just haven't got all of the intermediate steps written out. So let me... Here we go. So multiplying those numbers together, Let's just check I've got the right ones. Well, this first one is just 0.559 multiplied by 11.6 millimeters. So 0.559 times 11.6 divided by 1,000. 0.006. Am I getting the right numbers? Yes, I am. Okay, so we can work each of these out. UI star, the first one is 0.559 multiplied by 11.6 times 10 to the minus 3, which gives me 0.00648. UI2 is minus 0.001736. UI3 equal to minus 0.01859. UI4. I'm not going to bother writing the rest of them down because I've just done the piece of code and I'll go through them, but we can work these all out. What's important to note is that these can be negative numbers. Now that might be confusing because work should only be a positive should only be a positive quantity. When we're looking at real internal energy, this dl is force times the length divided by EA. So we could rewrite this first one up here as okay, so we can rewrite this. So no matter what the force is, length's always going to be positive, Young's modulus and area are always going to be positive. No matter what the force is, whether it's positive or negative, we always get a positive quantity coming out. This one here, this is going to be equal to, so this is the internal virtual energy, which is what we've just determined, is equal to the virtual force multiplied by the real force. Now these two can have different signs. Okay, and we very clearly have shown that in this case, and that's why I chose to do this case this way round. The real force is being applied downwards here, which means this member is under tension. Okay, the virtual force is being supplied in the opposite direction, so this is going to the virtual force going up here is going to cause a virtual compressive force in this member, so we get opposite signs, which means we end up with a negative value of virtual internal energy. Well, and the reason why we can have a negative value is because it enables us to determine displacements that might end up being negative, which means that the structure's moved in the opposite way to our sign convention. And that's what we're going to be showing. So we take all these numbers, multiply the virtual forces by the real extensions, add them all up. These are all members, add them up, and get the sum of the internal virtual energy is equal to By, it's going to be 30. Let me write this down. I'm deliberately not showing you the code for this just yet, okay? But that sums to minus 0.0349 joules. And this has to be equal to the sum of the external virtual energy. So the external virtual energy for this structure would be this force here multiplied by whatever the displacement is in this direction. So that would be delta By. And since our force was 1 Newton, this is equal to 1 multiplied by delta By. So it follows that delta By is simply equal to 2.0349 meters. Okay, and because it's negative, it means that it's moved down. So what we've done here is a really powerful procedure to talk about how this structure moves. Now this amount that it's moved down, this is because of P1 and P2. Okay, it's nothing to do with that 1 Newton force that we applied. That was just a placeholder, and it enabled us to relate this deformation to the energy stored within the structure. The P1 and P2, we only had to apply those loads at the beginning, and we said, okay, well, we'll work out what the reactions are and then what the extensions are of each member. Now, everything relating the forces P1 and P2 is captured within these values here, and then all we're doing now is we're using virtual force, or we're using the virtual energy as produced by a virtual force to relate this displacement here to all of the internal energy, and as a consequence relate this displacement here to these extensions here. Okay, so that's what this method does. We've done a really powerful thing here. I'd like you guys to go through this example using all of those numbers that I started with. So we started with this problem. We said it had a height of, did I even say that here? No, I might have just brought that in. Let's see if I copied it in up here. Did I bring it in? Oh, so I did. Okay, so I had a width of 10 and a height of 10 meters. Let's check I've actually done all those numbers in here correctly. Yeah, there we go. So we've got a cross-section area of 15 centimeters squared. P1 and P2 is 500 kilonewtons. Young's modulus for 180 gigapascals. I would like you guys to solve for these displacements using the same method. It's just the same procedure, but you've got to respectively apply virtual forces at Fbx, Fdy, and Fdx. And that's all that's going to do is it's going to change these numbers. So these are the bits that are going to change for the different virtual loadings. So these change with each virtual loading. These are going to be the same. Doesn't matter what you have, where you want to find a displacement. These numbers are the real extensions of every member due to P1 and P2 both being equal to 500 newtons. Oh, sorry, 500 kilonewtons. Now, this next bit, we're going to get on with next lecture. Okay? Now, this is deceptively difficult, or just more of an annoying problem to have to do. We need to use the force method for this. And we all sort of should have a good grip of what the force method is and how it does, and we're going to go through that again next week. But we need to determine a redundant reaction. And for this problem, that would be Fcx. So remember with this, we set it to be 0, which we've already done for this problem. We work out that displacement, which is why I said, let's put a force here, Fcx, because it's either going to be 0 or it'll be a virtual force of 1, and we'll work out how much it moves in this direction, or it'll be a real unit force of 1 in the other direction, and we're going to work out the displacements. What becomes difficult here is that we've got to work it out, the redundant reaction due to P1 and P2 being 500 kilonewtons. But what we're also going to have to do is that when we want to use the virtual work method to look at the displacements at these nodes, we're going to have to work out a virtual redundant reaction, okay? Because if we apply a force of 1 Newton here, that's going to be reacted by these 4 reactions. Now, because we've got a symmetric structure, we can check whether we've got the right answer by when we do these symmetric loadings, i.e. the vertical force here and the vertical force here, we should get sensible symmetric answers out. Okay, and we're going to go through that next week. But I want you guys to think about this. I want you guys to go through this. Okay, if you manage to solve for these if you manage to solve for the displacements, drop me a message on Slack, please. Show me you've done that, and then I'll congratulate you wholeheartedly, and I'll be really proud that you've got this far. This has hopefully been a good introduction to why we actually use the virtual work method and why it's important. It's pretty amazing once you get your head around what's really being done. I try to impress upon you guys my enthusiasm for it. We're taking a problem and we are saying all we care about in terms of how the external loads affect the structures are how each member extends on its own. And then we can just apply virtual loads anywhere and work out these displacements. So hopefully that's kept you guys interested. Please, please, please go through and do those little extra bits of work on here. I want to see your answers to those. So message me on Slack once you've done those. Okay, guys, I hope you're all having a wonderful weekend. I will see you all in the review on Wednesday. Okay, take care. So our free body diagram. Actually, when I did this earlier, I solved this using analytical expressions, and that's fine. So I'm going to say this is the width, and this is the height. Okay, width and height, because I didn't put the numbers in until the very end, but we can go through this anyway. So a free body diagram. So I'm going to put my applied forces. And I've got applied force here as well. So this reaction is going to be a force that we apply. So this is right, it's either going to be 0 when we're solving part 1, or it's going to be a virtual force if we're looking for the displacement here, or a virtual force in the other way if we're looking for the displacement that way. And then once we actually know the value of it, we'll just replace it with that. Okay, so this one here is FCX. And the 3 that I'm trying to solve for in fact, let's just say I'm not even going to bother talking through a lot of this because I'm fast forwarding anyway. Sum of forces in the x direction has got to be equal to 0, so made a thing here. These should have been R's and not, let's call these reactions, okay? So yeah, these are my reactions. They're still forces. I'm just going to call them reactions to distinguish the reactions that we're getting as a function of the external parts here. Which means I've got to change some of my nomenclature in here. Let's change this to an R. Oh no, let's not bother with any of that. Let's keep those all as R's. Okay. Method of joints. Let's start at joint A.